Hello, this is my Physics 2211 Lab 1 Constant Velocity. Introduction. The purpose of this lab is to observe the motion of some object moving at the same speed without changing direction. I will construct a computational model that accurately describes my observations based on physics principles. I will compare this model to observations by plotting the observed and the predicted position versus time on the same graph. These are the physics principles that were used in this experiment. I use Newton's second law, which states that the net force of an object is equal to the change of momentum over the change in time. Through this law, we can learn that if the net force is zero, the velocity of an object will be constant. The velocity update formula will also be useful. This formula states that the final velocity is equal to the initial velocity plus the net force over the mass times delta t. Finally, I will be using the position update formula, which states that the final position of an object is equal to its initial position plus its average velocity times delta t. As a quick preview of the results of the lab, I have found that the observed and the predicted motions were not identical. This is because we did not consider the small forces that acted on the object. This is a screenshot of the video that shows the displacement of my object in Tracker. I use Tracker to measure the position of the marker in each frame. It is important to mention that in the experiment, the system is the rolling marker, while the surrounding was everything else. With the information given by Tracker, we were able to get the conditions of the experiment. Firstly, the initial time is 0 seconds, while the time that passed each frame was 0.033 seconds. This means that the delta of time is 0.033 seconds. The initial position of the object was the vector 0.008500 meters, while its position after one frame is 0.02500 meters. So the displacement of each frame was 0.016600 meters. To calculate the velocity of the object through its motion, we needed to divide the displacement over the change in time, which got us the vector of 0.504400 meters per second. I added this information to my computational model. For instance, I added the initial time and delta t so that the model knew what time to use when updating the position. I also added the initial position and velocity of the marker. It's important to note that in this model, we have assumed that the net force of the object is zero, which explains why it is moving at a constant velocity. This is reflected in the change in the velocity update formula. The position update formula was also added. This is my calculation loop, which constantly updates the position of the marker after delta t passes. The model will only work when the time is less than or equal to 0.433 seconds, since this is how long my video is. This is the graph form after using the data given by Tracker and by my computational model. The orange balls represent the observed positions, while the green balls represent the predicted position. The x-axis is the time measured in seconds, while the y-axis is the position measured in meters. Initially, the observed and predicted positions were similar. However, as time passed, the position of the prediction increased more than the one observed. This means that the velocity of the observed object is decreasing, so a non-zero force is slowing the marker down. Some possible sources of errors were that we were only considering the movement in the x-axis and potential inaccuracies while using Tracker. Some additional questions we may have are: what if we flip the axis? Well, if we flip the x-axis, the position and velocity of the marker will become more negative as time passes, instead of more positive, although its magnitude will remain the same. If the other axis were flipped, there will be no change. Another question would have been if it was possible to know how many forces acted on the object. The short answer is no, since although we know about friction, resistance, weight, and normal force, we can't know every small force that acted on the marker. We can conclude that the observed position was not identical to the position of the computational model because we did not consider the forces that slow the marker down in the model, such as friction or air resistance. For this reason, after around 0.1 seconds, the predicted position was always more than the observed position. Thanks for watching.